Hello, here we got another Hooke's Law question. Yeah, these ones can be quite tricky, and people quite often go down the wrong route on some of these because they're so used to looking at everything in terms of forces when we've been through dynamics, which is not surprising. I mean, we've been putting forces at the center of everything in our motion and doing everything off of Newton's second law for pretty much everything we've had up until now. So when we get onto stuff with Hooke's Law, we're moving away from just looking at forces all the time and we're moving towards energy. We'll unpick a little bit as to why that is the case once I've gone through what the question is. So we've got a particle P of mass 5 kilograms placed at the point A. So let's mark it on here at A. So we've got some particle P there, 5 kilograms. We might as well mark the weight on with some 5G going down there. A rough plane inclined at 30 degrees, that's already mentioned, so we've got those on. Points Q and R are also on the surface of the inclined plane. QR is 15 meters, so we've got 11 meters down to R and 4 meters up to Q. And they're on a line of greatest slope of the plane. Right, okay. Right, wonderful. The particle is attached to two light elastic strings, PQ and PR. Right, so one up to Q and one down to R. One of the strings PQ has a natural length of 4 meters, modulus of elasticity 160 newtons. So we've got one string going up here, which is going to have one tension in it. So we call that TQ because it's going up to Q. We've got another one going down to R. So we've got a tension going down towards R. So we call that TR. We've got our normal reaction force on there, which we're going to need because we've got friction involved in things. Particle is released from rest at point A. Coefficient of friction between the particle and the plane is 0.4. Find the distance of the particle from Q when it's next at rest. Right, so on the face of it, you might think, well, we've got a nice force diagram here. Okay, we've got friction as well going on. Let's put friction in there as a separate arrow in that direction because it is going to start moving down the plane, the particle, so friction is going to be going the other way. And you might think, yeah, well, we've got a force diagram, so let's jump in and start doing a Newton's second law. The thing is, if you start doing Newton's second law, you're going to get a lot of terms related to distance because the two tensions here are going to be related to the position of the particle relative to R and Q. So in our force, the force is going to be a function of x, our distance away from, well, wherever we decide to measure it from. I mean, I'm probably going to measure distance from A, but you could measure it from anywhere. You could measure it from R, from Q. Doesn't really matter. But our force is going to be a function of distance. And then when we fill in the other side, we've got mass, and then we've got acceleration, which is the second derivative. It's a d2x dt squared. So this is the problem of going down a forces route when we're looking at Hooke's law questions, because we've got a second order differential equation. And okay, we can solve that. And when we move into oscillations, we will be looking at second order differential equations. But we don't always need to analyze things to that level of detail. You know, this will give us an equation. If we solve this, it will give us an equation of x as a function of time. So it will really describe some kind of oscillation that's going on as a x, our displacement time graph. And then, of course, we can work out velocity time and acceleration time and all things like that. But here, we just need to know when the particle is next at rest. So we don't need to go into that level of detail just to find out when something's at rest, because instead, we can look at energy. Or more to the point, we can look at conservation of energy. And that will just make things that little bit easier. So when we start off, as we always do with conservation of energy, we want to look at energy before, energy after. and then we can equate these two things. So what we've got initially is we've got no kinetic energy. We could set point A to be 0 potential energy, so that would be fine. We just need to set up what the elastic potential energy is that we've got in these two strings. So the string going from P to Q, well, that's at its natural length, because P to Q is 4 meters, and that's a 4-meter natural length string. So we've got nothing happening there. But the other one has got a natural length of 6 meters and it's been stretched up to 11. So we do have some elastic potential energy initially. So we need to put all of that in. So let's put that in now then. So we've got our elastic potential energy is going to be a half multiplied by the modulus of elasticity, which in this case is 120. Then we've got to multiply it by the extension squared, which is 5 squared, divided by the natural length. So that's 6. So that's our EPE at the start. Afterwards, we're going to have, actually, we're not going to have any kinetic energy because we want it to be at rest. So what would have happened is we've got a change in the gravitational potential energy. We've got the two new elastic potential energies, whatever they may be, for the two strings, and we've got the work done against friction. Right, so we've got a loss of gravitational potential energy because it's moved down the slope. So I can actually add that on to beforehand. So if it's moved, let's measure x from A. So it's moved some distance x down the slope, which means it's gone through a height of x sine 30 degrees. So our MGH, which we can add on here, is going to be 5 times g times x, all divided by 2, which is our sine 30 degrees. So that's our MGH. We've then got on the after side, which are all going to be positives, are the work done against friction. So that is going to be F times x, force times distance. And then we've got our two extensions. So for the string that's going from P up to Q, that x is the straight extension of the string. So we're going to have a half times 160, because that's our modulus of elasticity for that one, times x squared over 4, which is the natural length. And then for the other string, we've got a half times 120 times, so in this case the extension is going to be 5 minus x all squared, and then we have to divide again by the natural length, which is 6. Yeah, it is 6. I've picked up the right number. So now all we've got to do is solve this for x, and we're going to need to get F. So our friction, F is equal to mu r, and r is going to be equal to 5g cos 30 degrees. So that is 2/5 of 5g times root 3 over 2. So we've got a lot of things cancelled there. The 2's cancel, the 5's cancel, so we've got a g root 3 is our F. So F is g times the square root of 3. Right, let's start simplifying. There's a lot of stuff to try and simplify in all of this. So we've got a half of 120 is 60, divided by 6 is 10, multiplied by 25. So we've got 250. That's going to stay at the moment as 5gx divided by 2. We've then got afterwards our now gx root 3. Then we've got a half of 160 divided by 4, so that's 20x squared. 20x squared. And then here we've got 10 multiplied by 25 plus x squared minus 10x, just about squeezing that on. So just need to expand out that last bracket. Right, well that 250 is going to cancel with a 250 on this side, so we can get rid of those. We've got an extra 10x squared, so that takes us up to 30x squared. We've got minus 100x, and we've got plus gx root 3, and we've got a, well, let's put this other one on the other side, minus gx over 2, so that all equals 0. We can see we've got a factor of x in every term, and well, that fits with, it was at rest when x was 0. That's our starting point. So we're not losing anything by dividing by x because we're not interested in that solution. So let's go through dividing out one lot of x all the way through everything. And now we just need to solve for the x that's left. So x is going to be 1 over 30 times 100 plus 5g over 2 minus g root 3. Now we just need to type that into the calculator and get that x is 3.58 meters. Right, so what did it actually ask for? Let's just check. Find the distance of the particle. All right, from Q. Right, so we've measured x from A and we need it from Q. So therefore we've got distance, therefore distance from Q equals, we add on 4, so 7.58 meters. So yeah, if we'd gone down the forces route, then we're going to start hitting a lot of hurdles. We will get on to looking at that later on when we're looking at oscillations, because this particle is oscillating backwards and forwards. We know here we've got our two solutions of when the particle is at rest, once when it's at A, once when it's gone down at 3.58 meters, and the particle is going to be oscillating backwards and forwards between those. So when we take a closer look at oscillations, we'll be solving second order differential equations such as this to create these displacement time, velocity time, acceleration time graphs, which are going to be, they're going to be trig functions. You know, they're going to be variants of those. But we don't need that just to look at where we get these instantaneous points. You know, we could have done a similar thing with, well, when is there no acceleration? Yeah, if you're looking at specific cases like that, you can say, oh yeah, well, let's balance the forces then to see where we've got no acceleration, which is going to be where we've got our maximum velocity when there's no more acceleration, because the acceleration is changing sign, so the velocity has reached a maximum. But we'll start unpicking all of that and probably come back to this very question when we're looking at oscillations.